Ladies and gentlemen, welcome to this NASA Hyperwall Talk, Greenhouse Gases in Earth's Atmosphere, with Dr. Karen St. Germain, Earth Science Division Director at NASA. Let's give her a warm welcome.
All right. Thank you so much for choosing to spend a part of your afternoon here in the U.S. Center. I'm Karen St. Germain. I run Earth Science for NASA, as I often say, in fact, every time. It's the best job in the U.S. government. I'm thrilled to be here to share with you some of what we understand about how the Earth is changing, and we understand it because of what we measure and observe from space. So I'm going to walk you through just a part of the story. Oh, geez, I put the clicker down somewhere. I have no idea where it is. No, I think I left it in the secret room. I don't know. I'll be right back. I did. I left the clicker in the secret room. We're not telling you what else is in that room, but it is where the clicker was. Okay. Here we go. We're going to start with greenhouse gases because, we're at COP and that's really where a lot of the story starts. But before I get into the greenhouse gases, I'm going to talk to you just a little bit. Here, is that better? Is that better audio? I'm going to talk to you a little bit about how we make observations. So what you're looking at here, and the date stamp is down here, so this is just a short time ago. Is our NASA Earth Science fleet. This is really, each one of these arcs represents an observing system that is orbiting the Earth, looking down, making measurements. Some of these are making measurements of the atmosphere. Some are seeing through to the surface, measuring attributes of vegetation or attributes of the oceans, or maybe measuring the height of ice on Greenland or in the Arctic Ocean. So each one is each instrument is kind of a specialist. Although there are a few that measure more than one thing, and sometimes we call those our Swiss Army knives. But there's each one of these observing systems has a reason for being in the architecture. This is a graphic we call the swoosh, and it's showing you in a different way the NASA Earth Observing System fleet. Every one of these is denoting one of those missions. The ones in blue or green are actually on orbit today, looking down, making measurements. These in orange are missions that we're building that will launch in the future, and you can see the time hack on the outside of the swoosh. That's the launch date. So anything in orange or gold is in either development, if it's in orange, or if it's in gold, we're planning for it. We're doing the early definition. On the inside of the arc, these are all Earth Science instruments that are on the International Space Station. Clario Pathfinder is not yet on it, and actually we just retired the Lightning instrument. So, and then a lot of these satellites, they might be the size of an SUV or a bus. Some of them are as big as a coach bus, but some of them are the size of a shoebox, and the ones that are shoebox size are over here. So we have a lot of these instruments looking down, observing the Earth. Now I'm going to show you some of what they see. So I'm going to start with carbon dioxide. Now this is an interesting animation. Most of you know that there's a lot of carbon dioxide in the atmosphere. And so what we've done here is we're highlighting the low carbon dioxide and the high carbon dioxide. We sort of took out the stuff in the middle so that you could see where carbon dioxide is increasing, where it's at the high end of its cycle, and where it's at the low end. So here we are, we're getting into winter. This animation started at the end of the summer. As you get into the northern hemisphere winter, you start to see a lot more red. That's a lot more increase in carbon dioxide in the northern hemisphere winter. And that's, of course, because of two reasons. One, we're burning more, we're heating and so forth, but also there's a lot less vegetation to absorb the carbon dioxide, right? So that's why, carbon dioxide goes in an annual cycle globally, because there's a lot more land in the northern hemisphere than in the southern hemisphere, and more people. So the northern hemisphere seasonal cycle dominates the carbon dioxide seasonal cycle. And so here we're now in June. You can see as vegetation starts to grow, you can see the numbers once again start to decrease. So that's carbon dioxide in the atmosphere. And this is a similar kind of animation, but it's color coding the carbon dioxide by source. So you see over here, and we've got the captions over here, but the fossil fuel burning is in orange. That is dominant, right? And then burning biomass is in red. You see some of that over on the far edge. Land ecosystems in green and ocean in blue. And over land, the blinking dots, and over the ocean, the dots are showing you where carbon dioxide is being taken up. So sources and carbon dioxide in the atmosphere, the blinking dots are telling you where it's being absorbed. And this, it's understanding where the carbon dioxide is coming from, of course, that can point to ways to mitigate. In this animation, I'm showing you carbon dioxide on the left and methane on the right. And of course, carbon dioxide largely comes from combustion, right? So that can be in the form of transportation. It can be in the form of power generation. It can be in the form of, it can be in industrial plants, anywhere that combustion is happening. That's the biggest source of CO2. Methane, on the other hand, of course, comes from energy extraction, or it comes from decay, right? So they're both anthropogenic and natural sources of methane. But you can see, so some of the patterns look the same across these two. That's because you're seeing the atmosphere move, the patterns in the atmosphere are moving these gases around in the same way. So what you really want to do is look at where is it getting generated on the surface, and you generally see the methane and carbon dioxide getting generated in different ways at different times in different places. Of course, everyone in this room probably already knows that methane is, on shorter time scales, a much more potent greenhouse gas than carbon dioxide, but it has a shorter lifetime in the atmosphere. Carbon dioxide, of course, has a lifetime of hundreds of years, and so that's really why we talk about having to tackle both. Right? If you want to have an impact in the very near term, you want to go after methane. But in the long term, that doesn't buy you anything if you don't also go after carbon dioxide. So we track both. We make observations from space. One of the ways that we make information more accessible to people is, and more understandable from a science perspective, is we assimilate data into models. That helps us see the whole picture. So what you're actually looking at here is the output of one of the data-driven models. And that's really important when we talk about the models that we develop and we operate at NASA. They're all data-driven models. All right, so we've established we've got all this, we've got these greenhouse gases accumulating over time in the atmosphere. What happens? Well, they trap heat. All right, let's talk about heat. So all of our heat comes from the sun. All of our heat on the surface of the Earth comes from the sun, right? And then a portion of that gets reflected back out into space, generally by white surfaces, the tops of clouds, ice in the polar regions, that sort of thing. And the Earth also emits thermal energy. You know this, right? When you, if you were to look at the Earth through an infrared camera or goggles, you would see emission. So, for the Earth to stay at a stable temperature, incoming radiation has to be balanced by outgoing radiation, either reflected or emitted. Well, what we're seeing here is an imbalance, right? So this trace is, you've got seasonal cycles. Those are because the greenhouse gases have seasonal cycles, but there's a net increase in the amount of heat. That word anomaly means differing from the average. So we have an increasing amount of heat that's getting trapped in the Earth system. Where do you think that goes? Anybody? I know we've got the Ocean's crew in the back of the audience here. Yeah, 94% or so, thereabouts, of that excess heat is getting absorbed by the oceans. This has to do with a feature of water, right? Water has a high thermal capacity. And you know this because every time you put a pot of water on the stove to boil, it takes forever, right? You put on the heat and it absorbs and it absorbs and it absorbs and its temperature increases kind of slowly. That's exactly what's happening on Earth. The oceans are absorbing most of that heat. And the temperature on the surface of the Earth is increasing. This is an animation showing you the monthly temperature every year starting back when we first started recording weather. And I'm just going to let this run. So again, this is an anomaly. This ring right here is the average. So if you're inside the ring, it's cooler. Sorry, I keep moving the microphone around. Sorry. If you're outside the ring, you're warmer than the average. So watch what's happening over time. We're, in the 70s, we're right around the average there. Now we're starting to drift out. It's getting warmer. I won't tell you where I was in the 90s, but I was around. And here we go. So over that period, we got all the way out to the outer part of +1. And this is what that looked like over time. So a couple of things I notice. It's going nonlinear, right? It's the increase is increasing. All right. I told you that most of that heat is absorbed by the oceans. The thing is, it doesn't stay put, right? The oceans, even though flying over here, when you look down out of the aircraft, it doesn't look like the oceans are moving. It looks like they're rough on the surface. But there are many currents and eddies, and the oceans are very, very dynamic, both vertically and horizontally. This animation is showing you how the oceans, the color coding is temperature, and then you're seeing the currents, and it's showing you. And it is moving. It's slow moving from this view, but it's showing you how the oceans move a lot of that heat around the planet. And you can see, of course, there's warmer temperature. Most of that energy, or more of that energy, is getting absorbed close to the equator, right? In the low latitudes, but the oceans carry that energy around the globe. This is one of the reasons why we're seeing changes in weather patterns around the world. Because my friends at NOAA, and I don't know if I have any friends at NOAA, any NOAA folks in the audience today. Oh yeah, woohoo, NOAA! So my friends at NOAA would tell you that if you like your 5 to 7 day weather forecast, you should thank an oceanographer because all the weather starts with the oceans. So carrying heat around the globe, weather patterns are changing. All right, so what does that mean? Well, one of the things it means is when weather patterns change, soil moisture patterns change, right? Because all of the water that we use to grow our food, to drink, to do our laundry. All of the water we use on land comes from the oceans, and it gets delivered to us by the atmosphere. So, soil moisture, so what you're looking at here is soil moisture saturation, and you can see the monsoons and so forth. But the changes in soil moisture are having wide-ranging impacts for us who live on land. One of those types of impacts is on our food production. So one of the things that we did was we connected our climate models to agriculture models. You're looking at two specific ones here: wheat in the upper left, corn in the lower right. Wait, that's my left and right, so opposite for you guys. And I want to be really careful here. These are not predictions. Not predictions. What we did is we said, all right, when you want to model crop yield, there are really three knobs you can turn. The first knob you can turn is, what am I planting where? Am I planting corn? Am I planting wheat? Am I planting rice? What am I planting? And we focus on commodity crops generally in this analysis. So what am I planting where? That's knob number one. Knob number two is, how do I manage what I'm planting? When in the year am I planting it? Am I irrigating? When am I applying nutrients? All that sort of stuff. Those two knobs a producer can control. The third knob is, what's the environment? And that's where we come in, right? Because our climate models allow us to project out into the future the probabilities of particular types of events, precipitation patterns, and that sort of thing. So, in this analysis, we held constant what got planted and how it got managed. So we could isolate the likely impact or the possible impact of the changing climate. So again, that's why it's not a prediction, because we are changing how we manage agriculture. But what this kind of analysis can be is a really important tool for agriculture producers, because it can show you where different crops might get stressed first. And in the early part of the animation, and let me just start it over here, you see that in the very near term, we're already, particularly close to the equator, starting to see stress in corn production. We're starting to see some stress in wheat production close to the equator, but actually increased yields in higher latitudes. And then as this plays out, you see more and more stress on corn, and you see wheat doing well. So why is this? I am not trained in agriculture, but I will tell you what I understand about this. It has to, and why it plays out this way. It has to do with the fact that corn, in most places in the world, is already, it's where we plant it, it's already at the high end of its comfortable temperature range. Gets any hotter, and corn starts to really struggle to stay healthy. Wheat, on the other hand, we normally plant in higher latitudes, so it's not bumping its head up against its comfortable temperature ceiling. And wheat also uses carbon dioxide in the atmosphere a little differently. So it turns out that wheat is, when there's more carbon dioxide in the atmosphere, it uses that more efficiently, so it doesn't have to open up quite as much, so it doesn't lose as much water vapor. So increased carbon dioxide makes wheat more drought resistant. So you have sort of, in that particular plant, you've got competing factors. So that's the other reason why wheat does a little bit better. Again, this is just to show you the kind of tool we can start to create once we have observations that give us understanding that we can capture in a model that we can then connect to other parts of our ecosystem, our food production, for example, and that can help people make better decisions, figure out where they've got to invest their resources. Of course, the other thing that decreasing precipitation patterns do, and we have been experiencing this in the U.S., but it's true for probably in many of the places you live around the world, is an increase in the frequency and the intensity of wildfires. and also an increase in the duration of the wildfire season. In the U.S., most of the wildfires are triggered by lightning, so what we have is a situation where we have increased fuel loads, vegetation under stress because it's not getting enough water. Ooh, am I way over time here? No. I don't know. I'm looking down and the clock says red and it's 0 and I don't know. Somebody give me the high sign if I'm okay. Okay, I got the high sign. I can keep going. Okay, so vegetation under stress, dry fuel in the system, lightning strikes, wabam. And then one of the tricks is, how do I figure out how this fire is going to move? To do that, of course, understanding the weather is really important, the winds and so forth, but also understanding the nature of the fuel load is important as well. So one of the things that we're doing is really investing in our fire modeling, again, collaboratively with our friends in other agencies to try to get a little bit more proactive, a little bit less reactive when it comes to fires. Okay, I tried to bring you on a journey of the kinds of things we can see in space and how we understand how the whole system is working. One of the important things to say is that we have all these different instruments making different observations. I didn't go into the sea level rise story, but it's similar there, where you have different instruments making different observations, and they help you piece together the story of what's happening. But another thing that our instruments do is maybe help us solve the problem. So this is one of those instruments that we launched to the International Space Station. It's called EMIT. Sorry, this isn't the instrument. I'm showing you some data. I'll get to that in a minute. We launched this instrument to the International Space Station. This is one that was intended to map out the mineral composition on the surface of bare Earth. The idea behind it was, hey, if we know the mineral composition on bare Earth, that's where most of the atmospheric dust comes from, right? Wind blows across unvegetated regions, kicks up that dust into the air, and then how it behaves in the atmosphere depends on what it's made of. We don't have a way to know that unless we can trace it back to where it came from and know what that mineral composition is. So that's what this instrument was intended to do, is map out mineral composition on the surface of the Earth. The instrument's called an imaging spectrometer. That means it's a hyperspectral instrument. Hyperspectral instruments are generally, these are the Swiss Army knives. They can see a lot of things. It didn't surprise us because we've done similar observations from aircraft, but it was unplanned that we would have such clear pictures of methane emission. So we are now, in addition to all the science we had planned to do with this instrument, we are detecting methane emission I around the world. This happens to be one in, I think it's Carlsbad. So this one is in the U.S. And I show it because we're doing our homework at home as well, trying to address our challenges. But we provide all this data. It's all openly available for others to see that they've got. In many cases, it's a leak in a line somewhere. Sometimes they don't. The owner doesn't even know. So this happens to be, again, we talked about earlier, methane generally comes from extraction, right? So this is an extraction leak. All right, I'm going to leave you with a dashboard, and I'm going to actually ask you to watch this play out. This is another way of looking at global temperature over time. So again, months, years in the middle. And I'm connecting it here to increasing greenhouse gases. We didn't talk about it explicitly, but sea ice is shrinking. We've got some metrics down there. And I'm just going to watch this play out and see how you all react when you get to the end. Dramatic pause. Bang, bang. That's this year. Right? Really striking. It's not just that temperatures over, since April have been higher than all the other years before, but it's by a lot. So, this is for us, sharing this insight is important because none of us experience climate change as an average degree warmer or 2 degrees warmer. We experience it in these other ways with changes in our precipitation patterns, flooding, droughts, etc. But this is the sort of the precursor of what's coming. And look, I work for NASA, right? We are aspirational. We like to explore. And there's a tremendous amount of value to that. But this planet, the one we live on, this one's the gem. And everyone we know and everyone we love is right here. So this is the one we've got to take care of, and we're trying to use our special vantage point from space to help inform how we do that better. So with that, I am done. Thank you. So how are we doing time-wise? Do we have time for any questions?
We maybe have time for one short question or 2 short questions. So keep them short.
And if you ask a question, you get a sticker, I think. I don't know.
That's a good deal.
Only if Tyler still has stickers, though. Yeah. We do have. And it's the special Earth meatball. Ooh, that is a very special sticker.
So, what is the status of the NISAR mission?
The status of the NISAR mission? Yeah, so I didn't preview what's coming up. We have several new missions coming up. One of them is a very deep partnership with our pals in India, the Indian Space Agency, ISRO. We are together launching a mission called NISAR. It's a synthetic aperture radar mission. That will do a lot of things for us. Basically, if that's a new term to you, what a synthetic aperture mission synthetic aperture radar mission does, is it's very sensitive to changes in structure. So anytime something moves by as little as a centimeter, we can see it we will be able to see it with NISAR. So that could be earthquake damage. It could be a volcano, the land around a volcano starting to bulge. That you couldn't detect on the surface. And it can be changes in vegetation, like when a forest gets harvested. So any of those kinds of, I'll call them structural changes, this mission will be able to see. It will be launching in the new year, in the spring of the new year. So we are, it's all of the hardware is now in India. It's all been integrated onto the spacecraft, and we're in the final run up toward launch within in the spring of next year. So stay tuned for that launch date. Really exciting. And also, Nadia wouldn't forgive me if I didn't mention the instrument we're launching in late January, early February. It's called PACE. It is going to show us the biology of the oceans in a way that we've never been able to see before, and also teach us a lot about the interaction between the atmosphere and the oceans. You saw, and we all know that vegetation, trees, they harvest carbon dioxide from the atmosphere and turn it into growth, right, once you've added sunlight. Well, the ocean has plant life that does, or I call it plant life. It has life that does the same thing. Phytoplankton do the same thing. They play the same role. And they often get their nutrients from the atmosphere. So, dust and things blowing across the oceans. So we'll gain a whole lot of new insight into the ocean's role in the carbon cycle with the PACE instrument. So lots more fun to come. Can't wait to talk to you next year. Thanks everyone for coming.
Round of applause.